Okay, welcome. We're going to continue on here. Chapter 2 we're in. So last time we talked a little bit about chapter 1, and again, there's not too much out of chapter 1 that you have to worry about. Again, just kind of scientific method. We got into chapter 2, which is really measurements, sort of the main stuff here. So we talked about last time that when we do take measurements, we should always have a number and a unit. And again, the unit always really important to have when you write any type of measurement. It gives again people an understanding of what the number represents, not just a number by itself. We talked about different types of units. There's again the English sort of units. There's the metric units, and really the ones used a lot in chemistry, which is again a version of the metric system, which is those SI units. Remember that when we talk about something like kilograms, we're talking about a mass, right? Volume, liters, seconds, time, Kelvin, temperature. So remember that understanding what those units mean is also really, really important. We saw some important sort of conversions and equalities for different units like length, volume, and mass along the way. Um, we talked about qualitative and quantitative type of observations. Again, qualitative is just sort of general observations about what's going on. It's not measurement based or anything like that. And that's different than quantitative, which is pretty much all measurements. So quantitative sort of observation is really a measurement that you should record, obviously, the proper number of units, numbers, and to the right number of significant figures. We talked about temperature conversions. And again, if you want the temperature in Kelvin, which is a common one that we do a lot, that's 273.15 plus the temperature in Celsius. If you want the temperature in Celsius and you have Kelvin, that would be a temperature in Kelvin minus 273.15. As we talked about, pretty much these are going to be the major two sort of conversions for temperature that we will see the most outside of chapter 2. We also talked about degrees Fahrenheit, which is 1.8, the temperature in Celsius plus a 32. Also, if you want the temperature in Celsius and you have Fahrenheit, you're going to take the Fahrenheit minus 32 divided by 1.8. So remember that you do need to know how to do these conversions between these different units. And as I said, probably 9 times out of 10, it's going to be taking that Celsius to Kelvin is probably the conversion that you're going to do. Probably outside of that, going from Kelvin back to Celsius, probably the second most temperature conversion that you're going to do. We talked about doing temperature conversions and sort of significant figure rules, and they don't really follow strict significant figure rules. They follow really a general sort of rule when you're doing a temperature to temperature conversion. And as we talked about, whatever the original temperature value looked like in terms of how far the reading was, either to a whole number, first decimal place, second decimal place. When you do the temperature conversion for that, you take it to the exact sort of place. So if it was a whole number, when you do the conversion, you would convert it to a whole number. If it was to the first decimal place, you would convert it to the first decimal place. At the end there, we talked about scientific notation, which again has this general format. And this is a number between 1 and 10. And this is positive or negative, depending on which way you need to move that decimal point to get to a number between 1 and 10. So remember, it shouldn't be something like 10, 20, 100, or anything like that. It does need to be between 1 and 10. And more importantly, we talked about our calculators and making sure that we do use our exponent buttons, which looks one of these combinations in most people's cases. And remember that when you do hit your exponent button, it does represent the times 10 part of the number, which means you should not be hitting the multiplication button, shift log, or anything weird like that. You want to make sure, again, that you put these things in correctly. We also talked about other important buttons like our negative button, which, again, on most people's calculators, probably one of those two type of buttons. You do not want to, again, use the subtract button if you're trying to do a negative. Any questions on any of that stuff? Yeah. Yes, otherwise you're going to run out of fingers really quick, I imagine. Yeah. It has to be a basic scientific calculator, non-graphing. Yeah. Yeah. Okay. So pretty much if it has the exponent button and a log button, you're good for everything that we'll do in this class. Yeah. Yeah. I'm not exactly remembering the example we were talking about there. But yeah, so however, if you're talking about sort of like the prefix sort of example, is that what you're talking about maybe? Where it goes like kilo or something like that? Where it's 10 to the 3 or something like that? Okay. All right. So other questions on that? Yeah. Oh, this one here? This is if your calculator has that button. That's this. That's the scientific notation, the way the format should be. It depends which way you need to move the decimal to get to a number between 1 and 10. So like we had, I think maybe like 125, right? You need to go 1, 2 places, right, to get to a number like 1.25 times 10 to the 2. Yeah. And the 2 is how many places you need to move to get to a number between 1 and 10. And it's positive if it's really a large number above 1, like 125 is, or you move it to the left, and it would be negative if it was a smaller number, like we had 0.12. Just needs to go one place here to the right, and it'll be 1.2 times 10 to the minus 1. Good. Other questions? Okay. So why don't we do a couple examples here of punching these things into our calculators correctly, just to make sure. So I don't think we did that. So why don't we try 4.25 times 10 to the minus 4. Let's divide it by 3.2 times 10 to the 12. And why don't we do 7.8 times 10 to the minus 6 times 1.4 times 10 to the, we'll do 3. All right, so for each of these, punch them into your calculator, get an answer. I'll do it as well since I made them up. I'll see, we'll get the same answer. Look, so once again, if you were to punch this into your calculator, I would go 4.25, and at that point you would hit your exponent button. Again, that exponent button is going to take care of this part of the number. You then have a -4, which means you need to hit your negative button and 4. You then would hit your divide button, 3.2. Once again, your exponent button, which is going to take care of this part. That's a positive exponent, so no need for the negative, and hit equals. And if you do all that good stuff there, you should end up with, on your display, what I see is 1.328125, and on mine, it will say E minus 16. So that's sort of what the display says. So here we would go like 1.3 times 10 to the minus 16 would be our answer. Couple important things when you do look at your display, and commonly done. We'll talk about why we took, thank you, why we went to that many significant figures shortly, but a lot of times people will forget the exponent part. Yeah, when they look at the display, they'll just write the front number and kind of forget the back part there. If you have a different calculator, it may say times 10 to the minus 16 there on the back end, but it'll have something like that. Some calculators will even do a space between the front number and just the exponent part as well. So it's very common people kind of forget the exponent part when they write it. Also, when you do write it as an answer, it is times 10, not E. So don't write E as sort of, minus 16, write it as times 10 to the minus 16. Any questions on that one there? Obviously, if you had the one where we talked about with the will and sort of the times 10 to the end, you do have to put parentheses around each of those entries as we talked about again to put it in right. Same thing here. We're going to go 7.8. Once again, we're going to exponent button. We're going to negative button and we're going to 6. We're going to hit the multiplication button. 1.4. Once again, exponent button and 3 here. And that's going to give us 7.8 to the negative 6 times 1.4 to the 3. And it's going to give me 0.01092 in this case. And we would probably take it 0.011. And we'll talk about why that is here in a second. Yeah. Yeah. We're gonna talk about the rules, but the rule basically is it's the least number of significant figures. So that is pretty much the least number of significant figures. And remember also the something that we talked about, I think the other day as well. When you do write something in scientific notation, all the numbers that come before the times 10 part are significant. So that's how we know how many each of those numbers have. That's something that sometimes people, when they see a number in scientific notation and they're asked something like how many significant figures or something like that, a lot of times people will turn it into a decimal, which should still have the same number of significant figures, but sometimes they mess up by doing that. So again, if it's written in scientific notation and you need to know how many significant figures it is, how all those numbers before the times 10 part are going to be significant. Questions? Yeah. Yeah. If you put it in scientific notation, that's perfectly fine. You can leave it in decimal, or if you turn it into scientific notation, it would be that as well. So they're both the same. As I mentioned, I think the other day as well, you don't have to give the answer to in scientific notation unless it asks you to do so. You can, as long as it has the right number of sig figs that we're going to talk about. That's the more important thing. But I think we also mentioned that in certain cases, the only way you can get the right number of significant figures is to write in scientific notation. So either way in this case would be fine in terms of the answer. Also, your calculator may not give you answers in scientific notation all the time, right? Unless you have a program to do so. So just keep that in mind as well. Nor does your calculator give you the right number of significant figures, right, when you're doing calculations. All right, questions on scientific notation, how to punch it in? Okay, make sure for sure you do it that way. Again, if you find yourself pretty close to the right answer, but the exponent's off a little bit, then again, it's probably the way that you're punching it in. So let's take a look at each of these here. We want to write these guys in scientific notation. So once again, we do need to go a couple places here to the left to get us to the proper number between 1 and 10. And that'll give me 5.68762 times 10 to the 2. Once again, it's going to be positive because it's a large number. We moved it to the left and we'll talk about it as well, but all those numbers are significant, which is why we have to keep all those numbers. We shouldn't drop anything out. If you go from scientific notation to decimal form, you should not lose any significant figures along the way. So you should keep what is significant. Here to get to a number between 1 and 10, we got to go 1, 2, 3, 4, 5, and 6 places there. And that's going to give us 7.72 times 10 to the minus 6. Once again, it is not written a decimal, but it is assumed to be about there. So we'll go 1, 2, 3, and 4 places. 1.25 times 10 to the 4th. We'll talk about why those zeros are not significant in just a bit, and that's why we got rid of them here. And lastly, we will go one place here to the right, and that'll give us 1.35 times 10 to the minus 1. So important to make sure you don't lose sig figs as you go from scientific notation to decimal form and back and forth. And as we will talk about here, we'll know how to assume what is a significant figure in just a second. Any questions on writing that there? All right. So here, once again, we'll go 1, 2, 3, 4, and 5 places. Going to give us 4.25 times 10 to the 5th. Again, it will be positive as it is a large number. here, 1, 2, 3, 4, 5, 6, and 7. 8 times 10 to the minus 7. Remember, positive exponents for large numbers pretty much over 1. Negative exponent, small numbers basically below 1 is a good way just to remember how we get there. Once again, those zeros in the first one, not significant, nor are any of those zeros in the bottom one, and that's why they all got dropped, as we will talk more about in a second. All right. So let's talk about how we get to sort of significant figures and what is a significant figure. And it really all sort of revolves around measurements and taking measurements. So whenever we take a measurement, regardless of the type of measurement, there's always going to be some degree of uncertainty when you take a measurement. There's always going to be some degree of estimation that you have to make when you take the measurement. How much that is does depend on the piece of equipment that you're using, and it varies depending on the piece of equipment. Some are really good, have very small uncertainties. Others have pretty large uncertainties when you do it. So, for example, if we had something like this, like a ruler, action here, we'll call these centimeters. And let's just say we wanted to measure my arrow here. So when you look at a scale, be it a ruler, a graduated cylinder, anything with markings, there's basically two types of markings that you will see. They're sometimes referred to as large markings and small markings. And in this case, our larger markings is 1 and 2, which means our larger markings represent 1 centimeter. Now, we also want to figure out what the smaller markings represent. So we do want to count how many smaller markings there are between two large markings. And when we go to start to count, it's also important to count past the very last large marking. So when we go to count, we would start here. That's 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10 markings. So we do have 10 markings between the two large markings. And that means that each of the smaller markings in this case represent how much? 0.1 centimeters, right, is what each of these represent. This first guy would be like 1.1, 1.2, 1.3, 1.4, 1.5, 1.6, 1.7, 1.8, 1.9, and then 2 centimeters as we cruise apart there. So when we take a reading on any scale, there should be certain numbers that no matter who takes a look at it, everybody should agree that it is at least that much. So in the case of my arrow here, everybody should agree it is at least 1.4. And we definitely would want to record that. 1.4 would be what is referred to as all the certain numbers. Now, when we take a look at this, we could clearly see that the arrow is not perfectly at the 1.4 marking. It's not perfectly at the 1.5 marking. It's somewhere in between. And that is where the uncertainty in this measurement is going to come into play. That's where the estimation is going to come into play. And it does depend perhaps on whoever maybe takes a look at it. Now, for example, I may take a look at it and go, I feel it's like almost perfectly in the middle of those two markings. So I would record that as a 5. Somebody else may look at it and go, I think it's a little closer maybe to the 1.4. Maybe it's like a 3, or maybe it's closer to the 1.5. Maybe it's like a 6 or something like that. And this is what is referred to as the first uncertain number. And whenever you take a measurement, in addition to recording those things, you should also record the units, which is centimeters in this case. And I would record something like 1.45 centimeters as the proper measurement here. when you take a measurement and you do this and you record all the certain numbers plus that first uncertain number, that is pretty much what significant figures is. Which means this measurement that I just took has how many significant figures? It has 3 significant figures in this case. So that's really what significant figures are when you take a measurement and you record all the certain numbers plus that uncertain number. You basically will record all the significant figures that you need. Now, you could also talk about sort of the uncertainty in this measurement by taking the smallest digit or the smallest marking and divide by 2. So if we take this 0.1 and we divide it by 2, that gives us 0.05 centimeters. So sometimes people will record this as 1.45 centimeters plus or minus 0.05 centimeters as sort of the uncertainty of that measurement. For the most part, when you take a measurement like this as 1.45 centimeters, you're basically saying, I think it's 1.45, but maybe it's 1.46, maybe it's 1.44. It's usually like plus or minus 1, usually in most cases of that last digit is as close as you want to take a reading to. Yeah. Yeah, so that's basically what significant figures are in a measurement where you record all the certain numbers that everybody should agree upon that it's at least that. And that first kind of uncertain number are sometimes referred to as the estimated digit as to, where the uncertainty really lies. Yeah. Other questions? Yeah. Would I underline the 5? No. So for example, if you were going to take this reading, and for me, I don't really need you to do that part of it. Some people will, as you go through your chemistry career here, want you to put that plus or minus in your answers. I will, you would want to just record your reading as something like this, 1.45 centimeters. Again, this is how these sort of get sort of the precision there of your measurement or by dividing that guy by 2. Yeah. Other questions? Now, it does depend on sort of your piece of equipment as to how you should take a reading. So for example, let's just milliliters. We'll put a liquid in here. All right, so let's say we put a liquid into this graduated cylinder here. And by the way, when we do put a liquid into a glass, we typically will see the curvature of the liquid. This is known as the meniscus. And when we see that meniscus, sometimes it's easier to see in certain glassware than others, this curvature. What's really happening is, as we'll talk about in a later chapter, the attraction between the liquid and the walls of the glass container are stronger than the attraction between the liquid and itself. So what happens is that liquid on the side of the glass will actually start to rise up through capillary action, and you get this sort of meniscus that actually forms. When we take a reading, we always read from the bottom of the meniscus. And that's because without that attraction force, the liquid wouldn't rise up the sides. It would actually be down there at the bottom where it actually is. Not all meniscuses are like the U shape. There are certain substances that actually the attractive force between the substance and itself is stronger than the glass container. And they'll actually go the opposite way. It'll kind of make like an N going the opposite way. Probably the only one that you come across in most cases that will do that would be mercury, and you won't come across that because they take it out of labs now, so they're not in lab anymore, mercury. But mercury, actually, like in old mercury thermometers and stuff, you would actually see mercury's meniscus go the other way. In that case, you would actually read from the top of the meniscus because that's really where the liquid is. It's just coming in on itself because it's more attracted to itself than the container. So 9 times out of 10, 99 times out of 100, your meniscus is going to look like that sort of U shape. So we still want to do the same thing here. We want to take a look at our large numbers. And our large number on the scale is a 10 and a 20, which means we got about a 10 milliliter spread, right, between our large numbers. Once again here, if we take a look and count, starting past the last large number, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. We again have 10 small markings, which means each of the small markings in this case represents 1 milliliter, right? 10 divided by 10 is 1 milliliter. That would be 11, 12, 13, 14, 15, 16, 17, 18, 19, and 20. So once again, if we take a reading here from the bottom of the meniscus, in that case, we do see that it is at least 15, so we would want to record 15. Again, here's where the estimation comes into play. And once again, it doesn't always have to be 5, so maybe we feel it's a little less than half, so maybe record 15.4 milliliters. Once again, these are all of our certain numbers. This is our first uncertain number. And once again, in this case, we have how many significant figures? 3 significant figures in this case. Again, our certain numbers and our uncertain number. Once again, we can take the smallest marking and divide by 2. And again, if we take that, that's going to give us 0.5 milliliters. So sometimes people may write this 15.4 milliliters plus or minus 0.5 milliliters. Now, in most cases, you can take the reading to one more place past to the right of the smallest marking. So if we look at this particular one, smallest marking is 1 milliliter. We could take the reading one more place to the right, which is the first decimal place. If you take a look at the one we did before, smallest marking was 0.1. We could go one more place to the right to take the reading, which is 0.01 places. That's also what you could use this for. If you take the smallest mark and divide by 2, it tells you it's 0.05, which is 2 decimal places. That's how far you should take the reading to, right? If you take a look at the one we just did there, you divide it by 2, it goes to 1 decimal place. That's as far as we could take it. So if you want to kind of double check how far you should take that reading to, and you feel very confident in what the smallest markings represent on the scale, you basically could take it, divide by 2, and that's how far you should take the reading to. Any questions on that there? So what happens if I have this graduated cylinder? Bad quality control at the plant there. All right, so we got I got milliliters. All right, so we'll lay something up. We'll go back here. So large markings here is how much again? Between this and this is 10 milliliters. Small markings in this case represent how much? It does represent 2. If we count how many of the small markings we got going on in this case, we got 1, 2, 3, 4, and 5 only. And that means that each of the small markings in this case is going to be 2 milliliters, right? So that's like a 12, 14, 16, 18 situation. So now when we go take our reading in this particular case, we are now between 16 and 18. What is between 16 and 18? 17 comes between 16 and 18, I hope, yes. And we would actually have to record 17 milliliters in this case. That would have how many significant figures, by the way? It would have 2 significant figures. The uncertainty here is actually in which number? The 7, right? That's our estimated or uncertain digit in this case. In this case, there is no good way between that space to figure out where 16 stops, where 17 starts, right? And stuff like that. There's no way to do that. We could do that on the other one because it's just one number sort of difference between the 2 markings. So it's easy to go, okay, halfway through is halfway to the next number, something like that. But here, there's really not enough room to do that. Now, if you even follow our little divide our small markings by 2, we end up with 1 milliliter, which means 17 milliliters plus or minus 1 milliliter. And that's the best that we could do is go like, I think it's 17, but maybe it's 18, maybe it's 16. There's a lot more uncertainty in that measurement. Yeah, questions on that. So not in 100% of the time can you go one more place to the right of the smallest marking, but most of the time you can. And that's why it's really important to take a look at the scale there. Questions on that there. Now, let's go back to our original sort of ruler there. So we have an arrow here, and we can go right dead on that line. We'll go dead on that line. So once again, this is the same scale that we had on our first ruler. We have our large markings here, which is 1 centimeter. We have our 10 markings, I hope, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, which means our small markings here are going to be 0.1 centimeters. So if we go here, that's going to be 1.1, 1.2, 1.3, 1.4, 1.5, and so forth. So if you feel it's dead on the line here, you have some options as to what to record. We could record 1.4 centimeters. We could record 1.40 centimeters, 1.40000 centimeters. Extra zero is not always a good thing. Yeah, just add them on. Not so good. So we'll get rid of that. Is there a difference in recording one of those two leftover measurements? Yeah. There really is a difference on if you recorded one versus the other, and you may not think it is, and it's a very common thing. People hit right on a line and go, I'm just going to record whatever the number is and just get rid of something perhaps. So let's take a look at both of these digits here and these measurements and recording and what they really represent. So we now know that when we record these type of things, we can figure out significant figures. So sig figs on this guy would be how many? How many sig figs? It would be 2 significant figures. The uncertain number in this case would be? It would be the 4 here, right? So the 4 in that particular case. On this one here, significant figures there are 3. And the uncertain number here would be? It would be the 0, right? So when we kind of look at both of these measurements and try to see which one is perhaps the right one, when we take the first one, we're saying, I think it's 1.4 centimeters, but maybe it's like 1.5 centimeters, or maybe it's like 1.3 centimeters with, plus or minus 1 of that uncertain number, right? So basically I'm saying, I think, it's, somewhere in that ballpark. That's a pretty big range of uncertainty, right? And that's a pretty big range of that marking is really nowhere near any of those spots, right? The 1.3 or the 1.5. When I look at this measurement, I'm saying I think it's 1.40, but maybe it's like 1.41, or maybe it's like 1.39, right? And that's pretty much like right about there, right? Better measurement is? Yeah, and the reason it's a better measurement is you have the ability on that particular scale to actually go out to 2 decimal places, and you should do that. If you just drop off to 0, you pretty much made that measurement pretty crappy. Yes, a lot crappier than it should be. Yeah, and you made a really bad measurement with something that should be a much better measurement. So keep that in mind. Even if you hit something directly on a marking, and you have the ability to go, for example, to one more place, you should put the 0 there to maintain the proper number of significant figures and not make your measurement worse. Question on that there. Yeah. All right, so there's our ruler there. All right, so as we've been talking about, when we do record these type of measurements and those uncertain numbers, the first all the certain numbers and the first uncertain number, those are significant figures. By the way, the uncertain number or the estimated digit is not always the last digit that is written on a number, but it is the last significant figure that is written. So that's really important. A lot of times it happens to be the very last number is written, but it may not always be the last number that's written, but it should always be the last significant figure that is written. So that's really important to keep in mind when you're thinking about which one's the uncertain digit and the estimated digit. This brings us a good difference between two things, which is accuracy versus precision. When we talk about accuracy, that is how close a measurement is to the true value that's being measured. Precision, on the other hand, is how close a set of numbers are to themselves. So accuracy and being accurate is like if you know what the true value is, how close you came to what it should be, what the answer should be, basically. Precision, a lot of times we use for things like labs where you do multiple trials. So you do the experiment multiple times and see how reproducible something is, right? So do you get the same answer every time that you do it? So in terms of lab, a lot of times we look at accuracy by looking at something known as percent error. And for precision, percent deviation or standard deviation is sort of what we look at. Very easy example is the classic, we'll throw some darts at the bullseye, right? Very bad dartboard. So we're looking to hit the bullseye, which is in the middle, and I throw my darts and I hit one here. Maybe I miss with the board. I hit one here. Am I very accurate? I am not very accurate. Am I very precise? I am not either. I'm pretty much all over the place. Maybe I shouldn't be throwing darts since I missed the board. All right, but I go, hey, double or nothing in a friendly non-wagering type of situation. And I pick up my darts and my pride and I throw it again. And I hit here, here, and here. Am I accurate? No. Am I precise? I'm precisely not accurate, right? So you could do something crappily the same way every time, right? And get the same answer, but it's still wrong, right? So is it possible, for example, if you do multiple trials of an experiment, you keep doing the same mistake over and over the same way, you will get the same result, but that result is not very accurate, right? So you can be very precise, but not very accurate. Clearly, I'm going to go triple or nothing. I think I might be up to at this point. And I can collect my darts, maybe. And I'm going to throw my darts now, and I'm going to go boom, boom, and boom. Am I accurate? Am I precise? I probably hustled you as well, but I am accurately and precise, which is really the goal when you do experiments, right? You want to be accurate. You want to make sure you sort of get what you're supposed to, the true value. And it does need to be very precise so that it can be repeatable, reproduced, and stuff like that. Any questions on the difference between those there? All right, there's our dartboard example. Looks just like mine if you close your eyes. All right. So as we see there, inaccurate and imprecise, precise and inaccurate, and then obviously accurate and precise. All right. All right, so let's take a look at some of these here. So take a moment, figure out which one is the proper reading. I think the line didn't move, so we'll go with that. All right, so on that scale, let's figure out which one is the proper reading there. All right, so let's take a look and see here. So again, we want to kind of look at our big marking. So that's a 2 and a 3, which go with the bigger marking. So that again is going to be 1 centimeter. We count the little dots there, starting with this dot all the way to the 3. We got about 10 of them, which means our smallest marking should be 0.1 centimeter in this case. And this big guy here would be 2.5. Next would be 2.6 and 2.7. So clearly it is 2.6, should be certain. Once again, it is not exactly 2.6, and it does look fairly close to the next marking, right? So perhaps in this case, they went with a 9 would be good. Centimeters. So I'm thinking it's one of these two here. Now we could look at our sort of plus or minus thing by taking, again, our smallest number here and dividing by 2. And that's going to give us plus or minus 0.05 centimeters. So I'm going to go with D there as our right answer. Any questions on that one there? All right. All right, let's take a look at the next one. So take a reading on this one, see what you come up with on this one here. Again, the big numbers go with the big lines. See? All right. So in this particular case, we do have 9 and we do have 10, which once again is going to give us 1 centimeter difference. Also still have the 10 lines. So it's going to give us 0.1 difference between them. That's going to be 9.1. In this case, we can go to If we're not sure, we could divide that, and once again, we can go to 2 decimal places, which means that is where we should end up, just past our 9, but before our 9.1 in that case. Yeah, any questions on that there? All right, so let's take a look at the meniscus here. Take a reading and let's see what we got going on. If we kind of zoom in a little bit there to see it, take a moment and take a proper reading on that one. Okay, so let's take a look. So this is the 30 marking, this big guy. That's the 40 marking. So that is a spread there of 10 milliliters as our big marking. Again, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10 markings. So again, in this case, each of the small markings is going to be 1 milliliter. So that's 31, 32, 33, 34, 35, 36, 37, hiding back there. So obviously here we can see it is at least 36. We're going to read from the bottom of the meniscus as we can see here with our eye. And again, if you feel it is sort of maybe between those two markings, perhaps you will record the 5 and milliliters in this case. Here we would divide this by 2, which means if you did record sort of that precision there, it would be 0.5 milliliters plus or minus 0.5 milliliters. This has how many significant figures? It does have 3 significant figures. The uncertain number there going to be R5. Yeah. Any questions on that reading there? All right. There you go. Apparently, see, they thought it was an 8. There you go. I was scribbling in there. So again, they saw it was 8, but either one's fine. It is to the right digits and stuff like that. All right. Go. Now, this is a burette, which is something that we are going to use in lab a number of places. And on a burette, it's actually a little bit different. Up here at the very, very top, that's actually 0. And that is 0. And we actually will fill the burette from the top. So we put a funnel on it and fill it from the top. It actually will drop out the bottom. So when you use something like a burette, it actually has a different sort of scale. It actually increases as you go down. So that's like 0. This would be like 1. This would be like 2. So when you look at this sort of scaling, first off, if you are to the top, you should record 0 and not like 25 or 50 or however big it is in terms of its volume. So that's a very common mistake when people use a burette. We'd still want to kind of look at the dashes here between. So the large marking is 1 milliliter. We do have 10 markings here. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10 to here. Between it, which means each of the smaller markings is 0.1 milliliter. So in a burette, when you have 0, you have 1, you have 2. If you find your liquid somewhere in this range, it's actually 1 point something and not 2 point something. So it does increase as you go down. So here we could obviously see this is 28 and that's 29. So this is going to be 28 point something. Once again, not 29 since it drops out the bottom. So on a burette, it's sometimes people read incorrectly when they do that. By the way, we know as well, we take that divided by 2, we're going to 0.05 milliliters, right? 2 decimal places is typically where we record when you use a burette. So in this case, we should have something like 28.85 milliliters. And again, going to 2 decimal places because there are 10 markings, each one representing 0.1, and you could go one more place to the right on this. That also means if you fill it to the very top at 0 when you start, you would record 0.00 milliliters. So you would also want to obviously maintain those zeros even at 0 when you do that. Question on that. So that's kind of one of the only kind of pieces of glassware where the reading is kind of different in terms of how you do it. And we will definitely use it along the way here. All right. All right, last one here. Here's a burette as well. So take a moment here and figure out what it would be. Okay, so when we look at this, again, the big difference here between our big markings is going to be 10 milliliters. If we count the markings between, I'll go down here where the volume is it. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10, which means each of our smaller markings is going to be 1 milliliter. Once again, if you're not sure how far you should take it, you could usually go one more place to the right. You divide that by 2. You could take it to plus or minus. Basically, the first digit is how far you should take the reading to. This again is a burette, which means it is increasing as we go downward. And here is 21, and I believe right about there is 22, and that would be 23, and so forth. So you can see we are in that sort of between 22 and 23 sort of reading. And in this case, it actually should be D in this case, right? It would not be C in this case, as this farthest that we can take the reading is actually 1 decimal place in this particular case. Any questions on that? Yeah. We will be towards the end of the semester. I think it's like 21 and 22 experiment is what we did. And we'll use not really called a burette, but it'll have a similar scale in the gas ones as well. So we will be using this. And as you go to 1A and 1B, you'll use a burette a lot. Yeah. Yeah. Yeah, I think if we zoomed in, I think that's, and in terms of all those options that were on there, that's probably the best option there, as the 22 is really right about here, kind of where that line is. Again, you could have, if you felt it was just passive, did like 22.1, 22.2, something like that. But again, the importance there is just taking it to that first decimal place. Yeah.
It seems like measuring the empty space instead of this.
It is, because when you started here, basically, for example, if you started this titration, it would have been filled to like to 0. So basically, as you empty it, that's how much you put in there. Now, when you use a burette, typically you take 2 readings. You take actually an initial reading, like wherever you start, and you take a final reading. And that, when you subtract those 2, when you take the final minus the initial reading, that will give you the volume of liquid you added. So in this example, if we started exactly at 0, put in there 22 milliliters basically of volume. If we started at 5 and ended at 20, we would have put in there only 15 milliliters, right? 20 minus 5 will give you 15 is how much we put in there. So another really important thing when you use a burette is actually you take more than one reading when you actually do it. You always take an initial reading where you start, and you always take a final reading where you end, and you subtract the 2, and that gives you basically the volume that you actually added. And obviously, if you started exactly at 0, pretty much your reading is how much you added, because you'd be subtracting from 0. Yeah. Other questions? All right. So let's talk now, since we've talked about sort of what significant figures are, let's talk about the rules for counting significant figures and how we know what's a significant figure, what's not a significant figure. All right, so let's start with non-zeros. Non-zeros are pretty simple. They are always significant. And by the way, when we do count significant figures on a particular number, we always go left to right, and we start counting at the very first non-zero. So always when you're trying to figure out how many significant figures a number has, left to right, hit that first non-zero, and that's really where you should start to count. So in this case here, 1, 2, 5, 9, all of them are significant. So this guy would have 4 significant figures in this case. Now, zeros is really the ones that give people a pretty hard time. There are 3 different types of zeros that we come across in a measurement or a number. The first one is leading zeros. Those are not significant. They're just sort of placeholders. So for example, like we see here, 0.0049, we actually would not start counting until we hit the 4. And that's really where we should start counting. And then the 4 and the 9 are significant. And that would give us 2 significant figures in this particular case. So you could have 1,000 zeros to come before that first non-zero. They are all not significant until you hit that first non-zero number. And that's when you should start counting. Now there are zeros that are trapped in the middle. Those are sometimes referred to as captive zeros, and those are going to be significant. So here in this case, we would start counting at the 5. These zeros are trapped, which makes them significant. And then we have a 4 at the end, which is also significant. So this would be 4 significant figures. The last type of zero is the trailing zero, or the zero that comes at the end. And that pretty much is the one that gives people the hardest time. And the zero at the end is significant if there is a decimal place in the number. So zeros at the end become significant if there is a decimal place or point in the number. The decimal point does not need to be next to those zeros. It just needs to be somewhere in that particular number for it to be significant. So 600 written like this, there is absolutely no decimal point written in this case, which means the 6 is significant, and that is it. Yeah, that is the only significant figure there is. It'll just have one significant figure. Although we normally assume the decimal points at the end, if it is not written in terms of significant figures, it's not there. Yeah, so it doesn't count. You can't just assume that's there. Yeah. Is that the reason why yeah, the 6 is only significant in this case. If it was, for example, a measurement, that would be as far as you would be able to take that particular measurement. If those zeros were significant, the decimal point would be there. Yeah. The next one would then be 3 significant figures. And it would have 3 significant figures because this one's significant. These zeros become significant because the decimal point's actually written there. And yeah. So if it 600.0 would be how many significant figures you think? It would be significant here, right? These are significant. This zero is significant as well. Yeah, they're all trailing zeros. So that would be 4 significant figures if it was written like that. Yeah. So again, it doesn't matter how many zeros you got at the end, as long as there's a decimal point somewhere in that number, it's going to make them significant. If it's not written, it's not significant. So earlier we were talking about that the estimated digit, right, is not always the last number. So for example, if we took these two, we'll do the one that was just asked. The estimated digit in the first one is which number? Which one is the estimated? The uncertain digit is? It is the 6. It's the only significant figure there is, right? So basically what we're saying in the first one is, I think it's 600, but maybe it's like 500 or maybe it's 700, right? That's a pretty big crappy measurement. Yeah, if it was a measurement, that's a big room of error that's basically happening in that case. The uncertain digit in the second one is? The uncertain digit in the second number here is the last 0. Yeah, that one. Yeah. And that is saying, I think it's 600, but maybe it's like 600.1 or maybe it's like 599.9, right? So that's a much, much better measurement. If that was a measurement, a lot less room for error. So as I mentioned before, the uncertain digit a lot of times, or the estimated digit a lot of times, is the last number that's written, but it's not always the last number is written, but it should always be the last significant figure that's written. And in the case like the 600 there, the last significant figure written is 6. Yeah.
What if it's like 600 meters?
It would be. Yeah. Yeah. Because the units don't have a bearing on it. It's the actual number, which is how many significant figures there would be in the number. Yeah. So for example, if I had 0.0010040032100, how many significant figures in this crazy measurement if it was a measurement? I don't know either. I'm going to count myself, I think. I'll just write new numbers. All right. So, like I said, I don't know. It's just writing numbers. Let's see. All right. So, we're going to roll this way, and we're really not going to start counting right until we hit that number. That's our first non-zero number going on. So, that's significant. These look like trap zeros, which makes them significant. That's significant. A little bit more trap zeros, which are significant. significant, significant, significant. So far, 1, 2, 3, 4, 5, 6, 7, 8, 9. That leaves us these three at the end. Are they significant? Did you say no? Yes? That is both answers. One of them should be right. The answer is yes, they are, because way over here, there is a decimal point. Yeah. And again, the decimal point does not need to be near those zeros, just need to be somewhere in that number, which would then get us where we're at 9, 10, 11, 12. Yeah. So it would have 12 significant figures in this case. Yeah. It would be something like this. Yeah. They don't count. Yeah. How many significant figures would this number have? It would have two. So these trailing zeros don't count either, right? So pretty much trailing zeros, no decimal point, probably may not count. Yeah. If I did 12,000 like this, it would now have 5. Yeah. So now these zeros count. Yeah. So let's take this number, for example, written like this. Speaking of tie something else together here. Let's say I wanted to write this number to 3 significant figures. What should I write? So 12.0, anything else? Same number. All right, so let's take a look at these. We're looking for 3 sig figs, right? So this has how many significant figures? 3. Now let's just say I owed you $12,000 and I said, I'm gonna pay you 3 significant figures. Here's $12. Is that good? Probably not good. Probably not gonna make out the door, I imagine, right? So there's a very big difference, right, between 12, the meaning of 12, and 12,000, right? So when we try to go to significant figures, and we'll talk about with rounding in a second as well, we don't want to change the meaning of the number. So although that does have 3 significant figures, there's a tremendous difference between the meaning of those numbers. This has only 2 significant figures. If I do 120, that has 3 if I do it like that, but still not the same as 12,000. You remember earlier I said sometimes there are only one way you could get a number to the right number of significant figures. The only way we could get this to the proper number of significant figures is actually to write it in scientific notation. Yeah. Going 1, 2, 3, and 4. I now have the same meaning for that number and a reminder that all the numbers here before the times 10 part, right, are significant. And that would be 3 significant figures. So this is an example, for example, if you got that and you needed 3 significant figures, the only way you could really get to 3 significant figures and keep the right meaning for that number is to do scientific notation. Yep. Was there a decimal in that 120 that I crossed out? I think I did put one in there, which would show, yeah. Yeah.
Or one.
Are you asking, can you write 120 times 10?
0.
You cannot, because remember, scientific notation has to be a number between 1 and 10. So it can't be 12 on the front end of that. Yeah. So, and that's again a very common thing that sometimes people will do when they write in scientific notation is they'll go, remember, they'll go kind of go over 10 or less than 1. It's got to be at least 1, can't be 10 or higher. So you got to put that into that sort of format, which means really the only proper way that you could write it is 1.20. Other question? Yeah. Yeah. No, 12,000 is 2. I want to write that number in 3 significant figures is what I was trying to do. I want to turn that number into 3 significant figures. So the only way to do that is to write in scientific notation. That 3 significant figures is not saying that that number had 3 significant figures. Is if you got that as an answer, for example, but your answer needed to end up at 3 significant figures, how would you do it? It would have to be 1.20 times 10 to the 4 in this case, because I wanted 3 significant figures. And if I wrote 1.2 10 to the 4, it would only be 2 significant figures. Yeah. So the proper answer would be the one that's boxed in the middle there. Yeah. Yeah. Good.
I'm just trying to think of, you know, how many sig figs are like what, how you made a scientific notation.
Yeah.
So you said,
You'll know by, we're going to talk about rules when you do calculations as to how many significant figures you should have. So you'll know how many significant figures your answer should have based on the rules we're going to talk about in just a second. Yeah. All right. All right. Now, there are a couple different types of numbers. There are measured numbers, which are obviously taken from some type of measurement. There's also ones that are referred to as exact numbers, and exact numbers are obtained basically one of two ways. They're obtained by counting. So for example, if I had a bunch of pens on my desk here, I'm not going to do some type of measurement to figure out how many pens I have. I'm just going to simply count how many pens I have. Are there definitions like these guys, which are equalities? These are two things that represent the same amount of something but are in different units. So 1 inch is 2.54 centimeters exactly. 1 pound is 453.6 grams exactly. 1 foot is 12 inches. 1 mile, 1.609 9 pencils. By the way, some of these conversions you should know as well. Yeah, so make sure you put a star on them as you go through it. So make sure you know these guys. What's the deal with exact numbers? It really pertains to calculations. Things that are exact numbers can have as many significant figures as they want. So when we're looking at our answer after we do a calculation, if there is something that's an exact number, we pretty much just ignore their contribution. We don't even worry about them. So if something's considered an exact number, we're not going to worry about it in our calculation because technically they could have as many significant figures as you want. So that's sort of where exact numbers come into play. Measured numbers, we definitely want to look at the significant figures. All right, so let's take a look at each of these. Significant figures in the first one is how many? It is 3, starting at the 3 going across there. So that's going to be 3. This guy here in scientific notation has 4, right? This one here has 3. This one here has 1. And this one here has 4, starting at the 9 and going across, 0 at the end, significant because of the decimal place. Yeah. Any questions on any of those there? All right, so here's just some examples of measured versus exact. Obviously, if you take a patient's weight, that's going to be a measured. If you got 8 apples in a basket, you're going to count it. 1 kilogram is 1,000 grams. That's considered an exact measurement. Again, that's really one of those definitions. Yes. Yeah.
why would 10 grams be?
There's no decimal written in this number, so the 0 at the end is, yeah. So when you're counting significant figures, like I said before, when we look at sort of decimal places, there's kind of two things. It's when we think about it for significant figures, it has to be there for it to count. When we think about turning something from, say, decimal form to scientific notation, we kind of assume it's there, and that's where we start counting. But for significant figures purposes, if it's not written, it's not there. Yeah. Other questions? All right, so we touched upon this rounding, and again, we don't want to do any extreme rounding like we did with our 12,000 example there, right? So normal rounding rules apply. Anything 5 or higher, we're going to round up. Anything less than that, we're just going to kind of drop the digits. And again, we do not want to go crazy rounding that we screw up the meaning of the number by trying to get the right number of significant figures, like that 12,000 example there. So keep that in mind as you do it. I say a super common mistake, especially early on, is people should always be focused on sig figs, but they're overly focused on sig figs here, and they do that kind of crazy rounding where you end up with 12 instead of 12,000, and it's a very different meaning. So you just want to be careful of that. Remember in your head that you may have to write in scientific notation. All right, we want to round these to 2 significant figures. So let's take a looky here. So 2 significant figures is going to take us to the 5. We're going to look at the 7, which means we are going to round up in this case, and we will end up at 36 meters in this particular case. Here, second significant figure takes us to here. that means we're going to look at the 2 that's next door to it, and that's going to be less than 5. So we're going to drop it, which means this is going to be 3,800 grams, not 38 grams, right? Because again, that's a very different meaning. We do need the zeros to keep the meaning of it. Should I put a decimal point at the end of that? Should not, because then it would have 4 significant figures. So again, that's really important. Yeah. What's that? Yeah. So 2 significant figures would take us to the 8. And we need to keep the zeros to maintain what the meaning of that number is. And we cannot put a decimal point at the end. Otherwise, we'd have 4 significant figures. Yeah. Because those zeros would then become significant in that case. Second significant figure is here, which means we want to look at our 2. We're going to drop in that case 0.0026 liters. Here we do need the zeros in the front, right, to maintain really what the meaning is, and they're not significant anyways. And lastly, here we're going to go to the 2. We're going to look at the 8, which means we should round up, and that's going to give us 1.3 kilograms in this particular case. Yeah.
That's, but with the units, subtract 1, 2. See how
If we were going to add and subtract, we're going to talk about that in like one slide. Okay. Other questions? All right. So let's talk about that since we've been going around how we do it. Let's talk about the rules for when we do a calculation and we're adding and subtracting our multiplier and dividing. And that's basically the 4 things that we basically do. If you multiply or divide numbers, the answer should have the same number of significant figures as the number with the least number of sig figs. So if you multiply or divide, when you get your answer should have the same number of significant figures as whichever one had the least number of significant figures. So for example, here, if we took 125 times 0.10, forget about the answer at this point, but in terms of significant figures here, first number has how many? 3. Second one is 2, right? Which means our answer should end up with 2 significant figures when we multiply that guy out. If we divided 0.1100 divided by 12, top number has how many significant figures? It has 4. Bottom number has 2, which means our answer should end up at 2 significant figures. So if you multiply or divide, your answer should end up with the same number of significant figures as the one with the least. So 125 times 0.1 gives us 12.5 in this case, which means we should end up at 13 for the first one. If we do the second one, we end up with, on our calculator, 0.00916666667. This case, 2 significant figures would take us here. We should end up at 0.0092 would be the proper number. So multiplying and dividing, you look at how many significant figures there are in each of the numbers that you're multiplying or dividing. The one with the least is how many significant figures your answer should have. Question on that there. Yeah.
let's say it's 41 would the answer
It would be. So you do have to take into account if you're multiplying the same unit by itself, you do have to square the unit. Just like if you were dividing, you had like cubic centimeters divided by a centimeter, it would end up being centimeter squared. Yeah. So you do have to adjust the units if you are to, yeah. Now, when we add and subtract, we actually look at something different. So let's get more room here. When we add and subtract, we are looking actually at decimal places versus significant figures. So when you add and subtract, add or subtract, I guess, or both, I guess, you're looking at the number of decimal places. The number of decimal places with the least is how many decimal places your answer should have. So for example, if we took 1.250, we add it to 2.11, and we add it to 4.9. And we take that on our calculator there. We end up with 8.260. So here we're adding, so we're not looking at significant figures, we're looking at actually decimal places. This one has 3 decimal places. This one has 2 decimal places. This one has 1 decimal place, which means our answer actually should go to 1 decimal place. That would give us 8.3 on the round, right? When we round it. That has 1 decimal place, but how many significant figures? 2. Yeah, so keep that in mind because that's important. By the way, if one of those numbers was a whole number, we should take it to a whole number. Yeah, smallest number of decimal places is none, right? So take it to a whole number if it happened to be. Now, if you happen to do a bunch of these things together, which does happen, let's just say we took 1.25 times 3.1, we divided it by 1246, and then we added it to 0.111. Right? There's a lot going on here, right? So we probably would start up here with these guys, right? Which means we're multiplying. And that means significant figures, which technically means we're taking 3 significant figures times 2 significant figures, right? Which means the top answer should end up with 2 significant figures. The next thing you would do would take that number and divide it by the bottom, right? So you then would be dividing 2 significant figures by 4 significant figures, which means technically speaking, when you're done with this whole left side, you should end up with 2 significant figures, right? Would I round personally to 2 significant figures at this point? Probably not. I would keep the whole number, take it to a few extra digits, because I still have some calculation to do at this point, right? And then I would add it here, which means I would then be looking at decimal places. So for example, 1.25 times 3.1 divided by 1246 gives me 0.00310995. I'm just going to write everything on my calculator there. And what I know from the result of that calculation is 2 significant figures, right? Which means technically speaking, that's where I should end up, right? So I wouldn't round strictly at this point. Probably I would just take the whole number in my calculator. Some people keep guard digits. They're sometimes referred to as keeping some extra significant figures. So if you did want to round a little bit, maybe you keep it out to there. Sometimes people put a little line on top to know where we should stop in terms of the significant figures. I would then add this to my 0.111, and I end up with 0.114109952. So let's figure out what we should really end up with there. We know we should end up at 2 significant figures on our first number, which takes us to here, right? Technically speaking. And now we're going to be adding, which means should I be looking at significant figures? I should be looking at decimal places, which means this one goes to 3 decimal places. This one goes technically to 4 decimal places, right? So our answer should actually end up at 3 decimal places, right? So when we're all said and done, that is where we should end up. So if you're doing multiple calculations along the way, should keep track of your significant figures throughout the calculation, and you should really take it to a few extra digits along the way, not round too much, and then clean it up at the end. The reason you don't want to round too much is if you round significantly after each step, you're probably going to move yourself further and further away from the right answer. So it's good not to round, or at least take a couple of guard digits, a few extra digits if you do have to write the number down, and then keep track of everything, clean it up at the end. Any questions on that there? All right, we're wrapped up there for